Okay, so this is the third lecture of my advanced nuclear physics course. So yeah, throughout my lecture, I'm going to explain what is microscopic mean field approaches for nuclear many-body problems. And this time I will explain how to describe the so-called pairing correlations, which is related to superconductivity and superfluidity of nuclear systems. But before starting today's lecture, let me briefly remind you what was discussed in the previous lecture. So let me go back to this second lecture. So in this lecture, I explained the Hartree-Fock theory and density functional theory. And I like to mention here that last time I mentioned that this factor 1/2 is related to the spin degrees of freedom. But actually this is not just because of this. So to relate the density and the Fermi wave number, I assumed that the neutron and proton densities are half of the saturation density. So n0/half is here, coming here. So this is just because of the density of neutrons and protons. And here I just introduced why the non-relativistic treatment is justified. And yeah, throughout my lecture, I use the non-relativistic treatment. And yeah, last time I explained that what we'd like to solve is the many-body Schrödinger equation, but it is practically impossible. So we introduced some approximation to the many-body wave function, and that was the theta determinant. So, and it makes the Hartree-Fock approximation. And last time I, followed the derivations of Hartree-Fock equations. And the point was the Hartree-Fock theory uses the theta determinant for the many-body wave function or trial wave function for the variation. So we derived equations for the expectation value of the energy using the theta determinant. Yeah, I think those terms. Yeah. So this is the energy expectation value taken by the theta determinants. And after that, we take the variation with respect to the single particle wave function, phi star. And after some calculations, we could derive the Hartree-Fock equation, which is an integral differential equation. So which contains the direct term, which is a kind of one-body mean field potential, and Fock term or exchange term, which is a non-local mean field potential. And we solve numerically or iteratively this equation to get the self-consistent solution. So, but in practice, we use that kind of energy density function, which is related to the density function theory. And last time I explained what is the density function theory, and it is in principle related to the exact solution of the many-body Schrödinger equation. And behind this density function theory, what we have is a Hohenberg theory and theorem. So this I skip. So yeah, based on the Hohenberg theorem, which shows that there is a one-to-one correspondence between the wave function psi and the density, one-body density, we can conclude that there exists, at least in principle exists, an energy density function, so which is a total energy, but written as a functional of one-body density. And by minimizing this object, with respect to the density, we can get the ground state energy and ground state density. And to solve this variational equation, in practice, we introduce the constant scheme where we assume we introduce one body kinetic term and remaining part and take the variation with respect to the single particle constant orbitals. So this is really similar to single particle wave functions, but in case of DFT, it is just a kind of numerical object to represent the one body density. Yeah, but by solving this constant equation self-consistently, which is very similar to the Hartree-Fock equation, we can increase to get the exact energy and the density for the many body Schrödinger equation. And I showed that, yeah, this DFT works very well in case of nuclear many body problems also. So by solving the constant equation for the specific neutron and proton numbers, can describe various properties of finite nuclei throughout the nuclear chart, and also it can describe nuclear matter properties as well. So it is a very powerful framework. And yeah, and in the end of this lecture, last lecture, I explained the relation between the Hartree-Fock theory with effective interaction and the density function theory. So the point was, in nuclear physics, we have to use some kind of effective interaction. And historically, we started with this kind of zero-range contact time interaction, which contains these delta functions. So because of this fact, the Hartree-Fock equation ends up with the local equation. And also, we can describe the total energy with expectation value of the Hamiltonian as a functional of various kind of densities. And by regarding this energy density functional, this total energy given by the various densities as an energy density function in the context of density function theory, we can regard that the Hartree-Fock theory with scarm effective interaction as a constant DFT in the context of density function theory. So this is the kind of the reason why Hartree-Fock theory has been so successful in describing the various nuclear properties. So that was a digest kind of the first lecture, previous lecture. And today, I will introduce the pairing correlation. So in the Hartree-Fock theory, we just assume the theta determinant of the wave function. So we neglect any kind of correlations. So we will introduce one of the most important correlation, the pairing correlations. So this is the third lecture here. So the purpose of today's lecture is the following. So I will first explain what is the pairing correlations and why it is important. And then I will explain the basics of Bardeen-Cooper-Schrieffer BCS theory. So this is the most important, the main part of today's lecture. And then I will just mention briefly some generalized framework, which is the so-called Hartree-Fock-Bogoliubov theory. So it is actually more, more sophisticated as compared to DCS. So this will be just briefly mentioned. Okay, so the main purpose is to understand how to describe the pairing, the superfluidity and superconductivity in fermionic systems, especially nuclei, within the microscopic mean-field approaches. Okay, so let me first discuss similarity and difference between electronic system and nucleonic systems. Okay, so as you may know, the superconductivity was found for the electronic system, and the BCS theory was also first established to describe this superconductivity. Okay, so in the case of electronic system, the important ingredient is the effective attraction between electrons, so the so-called electron-phonon coupling. So probably you have heard about this kind of explanation. So in case of solids, there are some crystalline structure of ions. Okay, they are positively charged, and there is some conduction electrons, so which is negatively charged. So this K represents some kind of wave number of this electron, and the motion of one electron induce some kind of distortion or displacement of ions. And then when some ions are attracted by electrons, then their position may be, shrink around somewhere here. And then if we look at this density distribution, effectively, there is a positively charged region. So then another electron with minus K finds this positively charged region, and they attract to each other. So this kind of effective attraction between electrons are the key to explain the electronic superconductivity. So Cooper pairs, I will introduce later. The kind of Cooper pairs are formed between spin up and down electrons with opposite wave numbers with the help of lattice phonons of ions. Okay, so this is the case of electronic superconductivity. But in the case of nuclear systems, the situation is different. So in nucleonic superfluidity and superconductivity, we do not have ions. So the attraction is originated purely from the nuclear force. So as I mentioned in the previous lectures, so this is the case of the central nucleon-nucleon interaction, which has some repulsive core at very short distance, and there is an attraction at certain region, which is short-ranged up to 2 Fermi. And then, because of this attraction, they can form the Cooper pair. So without this kind of third particles ions, in nuclear systems, this attraction can induce the Cooper pairing. Okay, so this is the difference, similarity and difference in superconductivity in electronic and nucleonic systems. Okay, so this attraction strictly speaking, it is modified by nuclear medium effect, but essence is this attraction. Okay. So now let me show some evidences of the pairing correlations in atomic nuclei. So so the pairing correlations was already established very soon after the BCS theory. Okay, for the superconductor. So the theory of superconductivity by Bardeen-Cooper-Schrieffer was published in 1957. This is a famous paper. And then after 1 year, actually 1 year, less than 1 year. So this is July and this is January. So you see, these guys, Boer, Motteson, Pines, published this paper, the title is Possible Analogy between the excitation spectra of nuclei and those of the superconducting metallic state. Okay, so they took the idea of superconductivity from this BCS paper and found some similarity in excitation spectra. So this figure was taken from this paper, and yeah, it shows some peculiar behavior in excitation spectra. So okay, so this figure shows the excitation energy of first excited state. So this is the lowest excited state. So energy of the lowest excited state. And the horizontal axis is the mass number, so the summation of neutron and proton numbers. And for those crosses, you can see here, corresponds to the odd mass nuclei. So the neutron number or proton numbers are odd number. And those circles corresponds to even nuclei. So as you can see, there are clear difference between odd mass nuclei and even nuclei. So as you can see, there is an energy gap between odd mass and even nuclei. So in case of odd mass nuclei, the energy of first excited state is very low. This is in MeV, so this is 100 keV, so 0.1 MeV. But in case of even nuclei, they have some gap to excite the first excited state, which is about 1 MeV. So they discuss this is related to the Cooper pairing. So in case of even nuclei, all nucleons are forming Cooper pair, and to excite the nucleus, we have to break the Cooper pair. It makes this energy gap. Okay, so this is the first evidence that was already discussed in this paper, just after BCS paper. Okay, so now I will show other evidence. And I think I already mentioned this in past lectures. So here I show odd even mass staggering. So this is the nuclear masses plotted as a function of proton number Z for a specific mass number, which is 1 or 2. So you can see clearly two parabolas, and yes. So this blue circles corresponds to odd mass nuclei, and in these red circles corresponds to even nuclei. So if you compare these two parabolas, you can see some staggering behavior. In other words, even nuclei show systematically lower masses as compared to odd mass nuclei. So this is also related to the pairing correlation. So for even nuclei, all the particles can form a pair and gain energy due to pairing correlations. So it reduces the it enhances the binding energy, and nuclear masses are reduced. Okay, so another example is excitation spectra once again, but this is the case of tin isotopes. So tin is the proton number 50. So those are excitation spectra, as a function of Newton number n. So those are tin isotopes. And in case of even nuclei, so these red numbers, so those are even, and also let me mention that this proton number 50 is a magic number. So there is an energy gap for the proton energy, single particle energy. So protons cannot form a Cooper pair because of energy gap. So they are in the normal state. But in case of those neutron numbers, even nuclei, as you can see, there are energy gaps And in case of odd mass nuclei, you can see a lot of energy levels on top of these ground states. And we can plot this energy of the first excited states as a function of Newton number for these thin isotopes. And as you can see, this energy gap is very robust. So though all along this isotopic chain, you can find systematic energy gap between the ground state and the first excited state. And also, you can find that the spin parity of those ground state, even thin isotopes, are always 0 plus. So there are some small symbols 0 plus. It indicates the total spin is 0 and the parity is positive. So this indicates a J-pi, spin parity. And actually, not only thin isotopes, but also the majority of even nuclei show the ground state spin parity 0 plus. And actually, this is also related to the Cooper pairing. So actually, two nucleons form a Cooper pair, and those pairs have spin parity 0 plus. So because of this fact, the ground state of even nuclei, majority of even nuclei, show spin parity 0 plus. And let me naively, explain this 0 plus character. So here I show the schematic plot of different single particle wave functions. And so this figure was taken from the Rimshuk textbook. And okay, so in case of, let's assume the spherical nuclei, then we have the total angular momentum, which is the summation of angular momentum, orbital angular momentum, and the spin angular momentum. So this is the total angular momentum, which we denote as J. And as you have learned from the quantum mechanics, this angular momentum and also the total angular momentum can take several states, which is from minus J up to J. So 2J plus 1 possibilities. And so here I show the JG. So Z projection onto the Z coordinate, Z axis is denoted as JZ. So this JZ, so Z component can take 2J plus 1 values. It means that this orientation, so this length of this vector is the same, J, but it can change the orientation, changing the this projection, JZ. So now, in case of spherical nuclei, those energies are degenerated because the potential is spherical, so it doesn't depend on this orientation. But so as you may know, the nuclear force is attractive and short range. Okay, so to make the overlap of two spatial distribution of two nucleons, they prefer to form a pair between the same JZ, but opposite signs. So in those cases, the spatial distribution of wave functions are the same. Okay, so in those cases, two nucleons can acquire maximum overlap between the two and feel more attraction. So this is the naive explanation why they form a spin parity J plus 0 plus pair. So because JZ is the magnitude is the same, but the sign is opposite. And then as a result, they form the spin parity 0 plus Cooper pair. Yeah, so this is the one of the naive explanation why they form the Cooper pair with spin parity 0 plus. And it can be confirmed that if you look at the spin parity of even nuclei, almost all even nuclei shows the spin parity 0 plus. Okay, so those are the evidences. So now let me show some interesting consequence of the pairing correlation. So one of the interesting phenomena related to the pairing is the so-called backbending phenomenon. Okay, so let me explain what it is. So this is the peculiar behavior observed in the moment of inertia in the rapidly rotating nuclei. So this backbending phenomenon was proposed theoretically in 1960. So this is just after the establishment of BCS and this indication of possible analogy in 1958. So now, what is this? So they predicted that in case of highly rotating nuclei, the Coriolis force can break the Cooper pair. So as a result, in the ground state, they form a Cooper pair, but in rotating state, because of the Coriolis effect, the spins are aligned along the rotation axis, and the Cooper pairs will be broken. So that was predicted in this paper. Okay, and so this is the first experimental data, I think. So this was published in 1971. So this is the case of deformed nucleus dysprosium 160. And this figure shows the moment of inertia I with some factor as a function of the h bar omega squared. So, and omega is related to the rotation frequency. So now, so this left part corresponds to slow rotation, and right-hand side corresponds to fast rotation. And this dashed line corresponds to the moment of inertia associated with, assumption of rigid rotor. So now, in case of slow rotation, as you can see clearly, the moment of inertia is substantially lower than the rigid rotor value. So this is because of the fact that nucleons form the Cooper pairs. So they are in the superfluid or superconducting state. So because of this Cooper pairing, the moment of inertia is reduced in this way. But as the rotation frequency increases, this moment of inertia increases, and it approaches to the rigid rotor value. So this indicates that the Cooper pairs are broken by this rotation through the Coriolis force. So the prediction was confirmed here. But later, another experiment was published. Experimental data was published in 1972, and it shows some peculiar behavior as shown here. So in this case, other deformed nuclei, L beam and ET beam, shows some different kind of behavior as a function of the rotation frequency. So now, after breaking of the Cooper pair, it shows some backbending. This S-shaped behavior. Yeah, and this is kind of transition between the superfluid state and normal state. So yeah, so this, how to say? So this, quantum mechanically there are two kind of states with superfluid state and a normal state. and the transition occurs gradually, and it ends up with this kind of back bending shape. So anyway, so these are the evidences, experimental clear evidence of the presence of pairing correlations in atomic nuclei. So there are such phenomena related to the Cooper pairing. So others are kind of reactions, for instance. So when two nuclei collide, there are some transfer of two nucleons, and there are some enhancement of pair transfer because of the Cooper pairing. Yeah, there are many phenomena related to the pairing, and now I will explain how to describe those pairing correlations in microscopic mean field framework. Okay, so now let me introduce the BCS theory, the Bardeen-Cooper-Schrieffer. And let me mention that Cooper, Professor Cooper is still alive. Yeah, he's now 94 this year. So there's a possibility to meet him somewhere in the world. Okay, so in this lecture, I hope you understand what is this. So what is the properties of BCS wave function? So this is a so-called BCS wave function described by second quantized form. So those UK and VK are some factors related to occupation probabilities that I will explain. And this AK dagger corresponds to the creation operator for the state K and minus K. So this AK dagger here corresponds to the creation of the pairs, Cooper pairs. And now, if you look at this, you cannot see many things. So this is some abstract object, but I will try to explain step by step in detail what is the meaning of this wave function. So now I will, in this lecture, I will derive many equations using these relations between the creation and annihilation operators. So in case of fermions, this AK dagger and AK, as you know, obey anti-commutation relations. This curly bracket corresponds to this anti-commutation. And two annihilation operators and creation operators are anti-commute to each other. And if you, I will use this. So if annihilation operator acts on this vacuum state, it is 0. And also this A dagger is act on this glass state, then it is also 0. Okay. So I will follow in detail. So if you do not understand, please ask anytime you want. So first, let me calculate this norm of this BCS wave function. Okay, so norm is this overlap between two BCS states. So now I just put the definition that I showed previously in the brass state and ket state. And please note that this order is changed. A minus K and K and L and minus L because of the Hermitian conjugation. So now these products can be expanded in the following way. So this is nothing but the same, just the same. I just write explicitly what is this product, right? Okay. So now let me consider to reorder the operators. So now, for instance, this term contains the index 1 can move up to here, next to the term which contains the same index. So the reason why I can move this term from here to here without any factors is it contains the even number of annihilation operators. So they are anti-commute. So they have different indexes and they are anti-commute to each other. And since there are even numbers of operators, there appear always 2 minus sign or 0 minus sign, so plus sign is the result. So we can freely reorder those terms up to here to here. So if you do for all the terms, you can rewrite this equation up to here. But yeah, if you, yeah, okay. So this is just the rewrited form. So now let us expand these terms. So here I just expanded this parenthesis here, resulting in these terms. Okay, and the point is, yeah, you can use these relations easily. For instance, so this is the beginning, so I will follow carefully. So for instance, here you find a dagger, but you can operate these a daggers to this graph state, so it vanishes. In the same way, here you have this annihilation operators A, but it acts on this ket state, then it vanishes. So those terms containing UV will not remain here. So now what is remaining will be here. And if you use these anti-commutation relations, and then since those are the same k and minus k, you can find these equations. So when you interchange ak and ak dagger, it will generate this 1 minus ak dagger ak, as you know. And then we just expanded these terms. So there appear this factor 1 here, right? So this AA dagger just corresponds to this result in this one. And then the remaining is the term containing this A dagger A and these 4 terms. But again, it contains this A dagger at the left side or A on the right hand side. So it also vanishes when it acts on this vacuum state. So what is remaining is this UK square and VK square, which is associated with this factor 1 here. So this is the result. So when you take the norm of BCS wave function, you end up with this equation. Okay. And if we impose the normalization of the BCS wave function, okay, so yeah, if we assume that this norm is 1, then all this UK square plus BK square must be 1, right? So this is an important consequence. So this amplitude, UK and BK, satisfy this equation for all states K. And I will explain what is the meaning later. So now, this is a norm. And now let us calculate the particle number expectation value. So yeah, since the BCS wave function contains the product of A dagger, it contains actually various particle number states. So even particle number state, 0, 2, 4, 6, and so on. So the particle numbers are not the good quantum number, but only the expectation value is valid. So if we take the expectation value of particle number operator n hat here, and this is just a usual definition of particle number operator, but here I just for technical reason I just explicitly write k and minus k separately. But this is just a particle number operator, A dagger A. And now, what we should do is, we just put this n hat, the particle number operator here, and the rest is the same as before. So now, let's see. So again, the terms, okay, without this operator, can be summarized here, as I explained it, in the previous slide. So we can reorder those terms without this factor k. Okay, so only k, index k, related to this number operator here is remaining here, and the rest can be summarized here. So now we can use the properties of BCS wave function, I mean norm of the BCS wave function. So again, we can expand this, but this is the same as before. So it only provides UL square plus VL square. And then this is 1 because of the normalization condition. So actually, so this terms becomes 1. So what should be evaluated is only this term, which contains the index k. So I can write this like this. Okay, so now I will skip this explicit reordering, but the result is the same. So only the term with k, the same index k or minus k remains as a result of this reordering. So there appear 4 terms. So since there are 4 terms, so so since there are 2 terms, and each of terms will generate k and 2 because of that minus k and k. And then as a result, it provides so this each term corresponds to 1 and result in the factor of 2. So this you can, if you become familiar with this, then you can easily do that. So as a result, so the main conclusion is the following. The particle number expectation value by the BCS wave function is given by this formula. So this is the particle number in the BCS wave function. So now you can interpret this VK square as a occupation probability to be a paired state k minus k. So this is the probability for pair k minus k being occupied. And this factor of 2 corresponds to the pair. So each state k contains 2 particles because of the pairing. And by summing up these VK squares multiplied by 2, you can get the particle number expectation value. So VK square is the occupation probability. And in other words, the rest of the factor, the UK square, provides the unoccupied probability. So the normalization condition UK square and VK square equals to 1 provides these probability interpretation. And you can get this particle number expectation value. Okay, so those are 2 important properties of BCS wave functions. And now let us calculate the dispersion, particle number dispersion. So as I mentioned, the BCS state is not a good particle number state, but a superposition of different even particle number states. So we can calculate the dispersion, which is defined by this n square minus n expectation value of n squared. So this is the usual definition of the dispersion. Or delta n is so-called the fluctuation. Okay. So this n square here. So this is already calculated. This is just a particular number expectation value. So what we should evaluate is this first term. So this n square, n hat square can be written in this way. Okay, so this is a particle number operator, and we can just how to say this is the n square, and I just described explicitly the two terms. I mean, one is two. I mean, we have two operators, n hat and n hat, and then we have two indexes, k and another index. And then there are two possibilities. One is both operators in the parentheses has the same index or different indexes. Okay, so I just explicitly wrote the k equal L part and k not equals to L part. So the reason why I did it is this first term can be regarded as one body operator. So it is very similar to the usual standard particle number operator, but we just have this square here. And this second term can be viewed as a two-body operator. So we need to treat carefully. So now let's see how to calculate this k equal L, one body part. But it is very similar to the expectation value of particle number operator. So we just have this square here. So in the same way as the particle number operator, we can get this equation. And only the difference is this red colored parenthesis squared. Okay? And we can expand this. And since there are four terms, it results in 4. So in the case before, there are the factor of 2, and in this case, since there are 4 terms, we have factor of 4. Now, in the case of this two-body part, yeah, it is slightly different, but what we should do is the same. So the term which do not contain those two indexes, k and l, can be gathered in some way, in some place, and it becomes just a unity, 1, because of the normalization condition. And now what we should do is to evaluate this, but this is again, so we can discard these u terms because of this operation of A dagger to the kept state or A to the plus state. And you can count the number. So there are four terms. Yeah, 4 terms of UV. Let's see. So this so no no. So this is 2b. So 4 terms of b square. This here b and b and b and b, and there are 4 terms. So, and again, so if you do if you use anti-commutation relations, you can just find only k and k minus k will remain, and it provides the unity in the end, and you have 4. So let me summarize. So now what we did is to evaluate this first term. So this first term can be written in this way. And this is to recall, okay, so this second term can be written in this way. This is just the expectation value of particular number square. And now it can be written in this way. So this is summation of vk square, and it is multiplied by the same summation. And then you can again separate this summation over two terms, but one is the same index, the other is a different indexes, and you can find the same terms here and here. Since we subtract this expectation value from this, those terms are cancelled out. So the final result is the following. So the dispersion of the particle number expectation value in the vicious state can be given in this way. So this first equation describes this term. So this minus this. Okay. And now you can use the normalization condition uk square plus vk square equals to 1. So this 1 minus vk square can be written as uk square. And it results in this equation. So it means that, first of all, as I mentioned, BCS wave function is not an eigenstate of the particle number operator. So because we have dispersion. And this fluctuation or dispersion is originated from this fractionally occupied state around the Fermi level. Yeah, it means that, so in deeply bound state, it is just the occupation number is just 1. And but I will explain. But it becomes 0 in the unoccupied state. And in the vicinity around the Fermi level, both uk squared and vk squares are finite. And those fractionally occupied levels around the Fermi level makes the dispersion, contribute to the dispersion. Okay, so actually those around the Fermi level contribute to the pairing. Okay, so now, so far I just explained what are the properties of vicious wave functions, and one property is the normalization condition, and the other one is what are the meaning of vk square, and what are the contribution to the dispersion, particle number dispersion. And now you can calculate in a similar way energy expectation value as well. So now for simplicity, I will assume a simple schematic Hamiltonian without two-body interactions. I mean, only the pairing interactions presents. So this first term is a kinetic term, and second term is the interaction acting between Cooper pairs or pairs. So pair is formed between k minus k and such states. So those are pairing interaction. So let's take the expectation value of this Hamiltonian. So the kinetic term is very similar, as you may see here, as a case of particle number expectation value. So you can eliminate the rest of the terms, and remaining part is this. And again, this U terms vanish, and you can consider moving this A diagram A to the blurred state. And you can get this result. So, yeah, for instance, this A dagger provides 1, and A dagger provides 1, and the rest is A minus K A. Yeah, sorry, A minus K A. Yes. What? Is it correct? So both terms, yeah. So, yeah, here, sorry, so AK dagger vanish, and AL dagger vanish, and rest is A minus K and A minus L here, and here. So you have here. So, and this provides a Kronecker delta, and you end up with this. So this is again similar to the one-body particular operator, BK square times the matrix element TKK. Okay, and the pairing term contains 4 operators, so it is the similar. You can do the similar way, but it is a bit complex. But what you do is to just eliminate these U terms again, and yeah, there are states with 2 cases. I mean, you can find the same indexes, A dagger with the same indexes, and because of the fermionic character or anti-commutation relations, those terms vanish. And then you can rearrange those remaining terms carefully, and you just get this equation. Okay, so it contains VK square and UV terms. And now, here I just rewrite this second term slightly. Using just equality. So this shows that, so this, here so we have to do it to eliminate this. And you can expand this again to get the term with, I use here, so it contains the term with the same index and different indexes as I did before. And you can use this relationship, UK square, VK square equals to 1 minus VK square times VK square. It resulted in these 2 terms, here and here. And then you can find here and here, this term and this term are the same. And you end up with this equation. So z minus z times this term, this is here, and the rest is vk to the power of 4. Okay, so why we did this expected calculation? So this is because, again, we want to perform the variation to derive the BCS equation. Okay, now in this way, you can get the energy expectation value of the BCS state for the simplified Hamiltonian. Okay, so now let us derive the so-called BCS condition. So if you agree with this conclusion we obtained so far, the first kinetic term here provides the B square times TLL here, and this pairing term provides this second and third term here. And now we introduce this constraint or some Lagrange multiplier minus this lambda to fix the particle number expectation value. So without this, we cannot get specific particle number states. But in this way, by adjusting this lambda, this Lagrange multiplier, we can control the particle number expectation value. Okay, so now we will perform a variation with respect to U and V. Okay, so these U and V are in the vicious wave function, right? And we will determine those coefficients through the variation principle by minimizing this energy expectation value with this particle number constraint. Okay, but now please note that U and V are not independent. They are mutually related through the normalization condition. So, right, the U square times V square, U square plus V square equals to 1. So you can perform variation with this in this way. So first one is just simply take the variation and this derivative over with respect to V. And the other one is take the variation for U, but so take the variation of U, but you have this factor here. So since U, because of this normalization condition, you can get UK equals to square root of 1 minus VK square. So if you take the variation with this, take the so this you take this derivative with respect to V for this U, then it will generate this 1 over this U, right? This is square root. It will be the minus to the power of 1/2, and this derivative for this minus VK square. And it generates this factor here. Then this, you can put this expectation value to this right hand side and take these variation, derivatives as written here. And then you can easily do it. So the first term becomes this, right? And so for instance, this, for the VK star to the power of 3 comes from here. And then the rest is here. And since this second term contains V and U, you have these two terms associated with these two terms. So these are just a derivative of these U and V. And then you can just write down this equation into this form. So here I just move this G to the power of G, for the term here and here. And I just use the condition. So I just introduce the delta, the so-called pairing gap, which is defined by this G. G is a coupling constant, which is the strength of the pairing interaction here. And the factor proportional to UK, VK, UV. So this is the pairing gap, and you can use this G times this summation by delta, and you can write down in this way. And because of the variation condition, it must be 0. So this is a stationary condition. So the point is, this is the result of variation, and this equation determines what is the U and V that minimize the total energy of the system. Okay. So this is the so-called vicious condition, which is a result of variation. Yes. So yeah, I just rewrite this equation in this form. Okay. So now, yeah. So now we can get the vicious equation. So as I explained, this is the result of variation, the so-called vicious condition, which determines the vicious amplitude U and V, UK and VK. So we can rewrite, this equation, or we can solve this equation analytically. Yeah. So yeah, you can use usual. You can rewrite this equation for UK square and VK square, and you can derive this equation. And this indicates that when the delta pairing gap becomes 0, then, for instance, so in case of delta equals 0, then the VK, yeah, this term becomes 1, and this VK becomes 0, right? And minus. It depends on this. So when EK is, so lambda was introduced as a Lagrange multiplier, but lambda contains the meaning of chemical potential. And depending on the energy and the, energy, this epsilon is a single particle energy. And when epsilon is smaller than chemical potential lambda, then this second term becomes negative -1, and it will result in 1. So VK square is 1. So occupation is 1. Occupation probability is 1. And when the chemical potential, is smaller than the single particle energy, then it becomes 0. And opposite is true for UK amplitude. So now, as you can see, without pairing correlation, delta, the occupation probabilities and unoccupied probability has a step function form. So it is just like a fermionic, normal fermionic occupation. Okay. But when delta becomes finite, then this distribution somehow becomes in this form. So with finite delta, the occupation probabilities VK square becomes less than 1, even for the states with single particle energies below chemical potential. In this way. So this is due to the pairing correlation and pairing interactions. So the pairing interactions are active for the states around the Fermi level, and some part of occupied states are excited up to the states which were initially unoccupied without the pairing correlations. Okay, so now yeah, using these relations, you can calculate. I mean, just take yeah, calculate this left-hand side with those equations. And then you can just use, you can see the difference is minus and plus sign. And yeah, you can do it in this way easily. And then, yeah, you can just rewrite equation in this way, in this form. And then, why I did this is to rewrite to get the gap equation, the so-called gap equation. So the definition of the pairing gap is here, and which is given by G pairing strength times the summation of UV. And UV can be written in this way using these equations. So the pairing gap here can be given by this equation. So delta can be written in this way. So this is the equation to determine the pairing gap delta. And the important fact is to derive this equation, we use these equations for the U and V. And remember that these equations were derived by variation principle. So this solution is a result of variation, and using this conclusion of the variation, we can get this equation. So this solution of gap equation automatically satisfies the variation condition here and here. And also we can, so by solving this gap equation, we can determine for a given chemical potential and single particle energies, what would be the pairing gap delta. And in addition to this, we can determine what are those occupation numbers, probabilities, Vk. So probably this should be square. Yeah, so this particle number, as we derived, particle number expectation value can be given like this. And yeah, so this here should be Vk square. But you can use the equation here and here. So you can solve those two equations simultaneously. So by using this equation so you have already assumed that you have single particle energies epsilon k for some states. And then using this second condition, you can adjust the chemical potential to get correct particle number for a given delta. Then you can fix the chemical potential for a given delta to get correct particle number. And then using this chemical potential for this given single particle energies, you can solve this gap equation to determine delta. So it updates the delta, and then once again you can solve this particle number condition for this new delta to determine the chemical potential, and until you get the convergent result, you can repeat this calculation. So in this way, this gap equation with particle number condition, we can determine the value of Vk and Uk and pairing gap delta. Okay, so this is important equations as a result of this wave function. So I just like to mention if you have some. Okay. So as I mentioned, by solving the Hartree-Fock equation or constant, okay, let's say constant equations. Okay. Plus the constant that I introduced in the beginning, in the previous lectures. So this is a constant equation, and as I explained, the constant potential can be obtained by, this potential depends on the density, and as a result, it provides some kind of one-body potential, and inside which we have a single particle state, some single particle states, and it is occupied in this way. And each of the levels has, as I mentioned, in case of spherical nuclei, 2J plus 1 degenerate state. But anyway, we have this kind of single particle energy levels as a result of, by solving a constant equation, we can get this potential and single particle energies. And then it provides us what is the single particle energies, these single particle energy levels. Then having those single particle levels at hand, we can solve the BCS equation. As I mentioned, we can determine the chemical potential and also solve the gap equation. And we can introduce, for instance, so in the last lecture, I didn't introduce this occupation probability, but in case of in this case, we can introduce in this case, the occupation probability times this. So in this way, the density, in the Hartree-Fock case, the occupation probability was 1. Simply, the occupied state is an occupied occupation probability 1. But in case of if we have pairing correlations, this occupation probability can be changed as shown there. And in this way we can modify the definition of various densities using the occupation probabilities from the BCS equation. And then we can get the mean field potential and single particle energies and solve the BCS equations. So this is in nuclear physics community, this kind of method is called Hartree-Fock plus BCS. So in this way, we can combine BCS theory with this mean field microscopic description of atomic nuclei. So this is one way to introduce pairing correlations in the description of microscopic description of finite nuclei. Okay. So, but in the rest of this lecture, I will just briefly introduce a more sophisticated approach. So in this case, the pairing gap equation is somehow externally or additionally introduced to introduce the pairing correlations through the occupation probabilities. But we can actually develop a more self-consistent framework to describe not only the single particle states, but also the pairing properties based on within a single framework. So it is the so-called Hartree-Fock-Bogoliubov theory, HFE theory, or in the case of condensed matter physics, it is known as Bogoliubov-Dojan theory. So they are Hartree-Fock and Bogoliubov. Okay. So, but in this lecture, the derivations are more complicated and lengthy. So I just skip the derivations and I just give you the idea of HFB theory. So before explaining what is HFB theory, yeah, let me mention one thing. So in this lecture, you have learned what is the properties of BCS wave functions. And the BCS wave function was written as a product of UK plus DK A daga A daga. But yeah, it was not clear by looking at that equation. But by taking various expectation values, we could learn a bit about the properties. But actually, we can interpret the BCS wave function, or BCS state, in a different way. So it is the picture of K-psi particles. So I don't introduce the derivation here, but you can look for the operator that satisfies this property. So taking the BCS wave function, BCS state, and here this operator is not A, alpha K. So this annihilation operator is a vacuum of BCS wave function. So when it acts on the BCS state, it becomes 0. So you can, for instance, look for this alpha K by a superposition of creation and annihilation operators. And you can determine through the commutation, anti-commutation relations, what is the factor. So what will be the factor in front of those creation and annihilation operators? And then you can derive this condition. So alpha K, this is the annihilation operator of the K-psi particle, is given as a superposition of UK AK minus BK AK minus K daga. So here, yeah, so be careful that this K-psi particle with index K, this is the annihilation of K-psi particle index with index K, contains annihilation operator AK and creation operator A minus K. So it is because the creation of minus K, or annihilation, annihilation state K can be related to creation of minus K. So, or I'm saying that the particle hole correspondence. So if we have hole of the occupied state, then it can be viewed as a creation of a particle. I mean, I'm mixing. So if we create a hole in the K state, we can view it as a okay. So if we destroy particle with state K, it can be viewed as creation of a hole with minus K. So anyway, so I'm saying that this index is somehow opposite. So anyway, those K-psi particle creation and annihilation operators can be given as a superposition of particle and whole states. I mean, A and A daga. Okay, so, and this BCS state can be given as a vacuum of this K-psi particle. Okay, so this is another interpretation of BCS wave function. So in the HFB theory, we generalize these K-psi particles as much as possible. Okay, so in case of HFB theory, we define a new vacuum, HFB state here, which is a vacuum of K-psi particles, which is different from this BCS K-psi particle, this beta. So this beta is given by superposition of A and A daga. But as you can see, here we take the summation over all states. So in that case, the K-psi particles was only the superposition of the same K or minus K, K and minus K. But in this case, we mix all the creation and annihilation operators. And we just require a variation condition to determine this coefficient U and V. So this is the idea. So this so HFV vacuum is a vacuum of K-psi particles, and this K-psi particles is very much generalized as compared to VCS K-psi particle. So by taking the variation, so you can again calculate the energy expectation value and then take the variation with respect to U and V. You can derive HFB equation. Yeah, so these are just a condition. So this is just the idea, you see an idea. K-psi particle, which can be written in the matrix form, and those operators obey the anti-commutation relations. Okay, then I think I will skip the details, but you can take normal standard Hamiltonian like this, one body part and two body part, and then you can take the expectation value, and then you can derive these equations. And if you are interested, you can look at this textbook by Ling-Shuk, for instance. There, everything is written. So those are just the details. But in this case, we have this gamma, which is similar to Hartree-Fock potential. This is a mean field. Has a meaning of mean field potential. And also delta. Delta is related to the pairing gap. But importantly, in this case, both mean field and delta is determined by the interaction itself. So this V bar coming from this two-body interaction, and just taking the variation, we can get the mean field and delta pairing field. And by taking the variation, yeah, we can get the so-called HFB condition. So yeah, so far I didn't explain the Hartree-Fock theory in second quantized form, but in case of Hartree-Fock theory, it will be just very similar. So in case of Hartree-Fock theory, it will be just something like this. So H is related to the single particle Hamiltonian in the second quantized form, and rho is a density matrix, and the commutation relation is, so both are commute each other. So this is a Hartree-Fock case. This is equivalent to the Hartree-Fock equation. But in case of HFB, we can eventually derive the same, very similar equation, but generalized in this way. So it has each of the matrices H and R, given by matrices, and this HFB condition provides this HFB equation, the so-called HFB equation. So by solving this equation, we can determine U and V, which is the coefficients for this generalized K-side particles. And yeah, by solving this equation self-consistently, I mean, again, V determines the mean field potential and UV determines the pairing potential, and we solve this equation, and then we can get a new set of U and V, and we can update the mean field and pairing field, and we can repeat this procedure until we get a convergent result, self-consistent result. Okay. And then I think this is the almost end of the this lecture. Okay, so let me summarize. So in this third lecture, I first introduced what is the pairing correlations and what is the properties of pairing, Cooper pairs in nuclear systems. And there are many various evidences of pairing correlations in atomic nuclei. So I just, in this lecture, I introduced some odd even mass staggering, and this energy gap of the first excited state for even nuclei, and spin parity of the ground state of even nuclei are almost all even nuclei shows 0+. And the peculiar behavior of the moment of inertia, and which is related to transfer reactions. And in the 6th or 7th lectures, I will introduce some consequence of the pairing or superfluidity in case of neutron star matter. So the pairing correlation also affects stellar properties like neutron star cooling and the pulsar glitch, which is the sudden change of the rotation frequency of neutron star. And so there are many evidences of the pairing correlations. And I introduced what is a BCS theory. So, and I showed that pairing correlations are described by mixing the particle and Hall states. So this mixing can be viewed as a K-side particles because the BCS wave function is the vacuum state of the K-side particles which mix the particle and Hall. Or we can view these properties from the fractional occupation at the Fermi level, which makes some part of occupied states excited with partial excitement, and it becomes some fractionally occupied states around the Fermi level. And those states contribute to the pairing. Because the delta pairing gap is proportional to the factor UV, and this UV component only becomes finite around the Fermi level. And also, the particle number dispersion tells us this dispersion is also contributed from the states around the Fermi levels, and this is important properties in the BCS or generally in general pairing phenomenon. Okay, and finally, I just briefly introduced what is the HFB Hartree-Fock theory. And as I mentioned, it is a very complicated or generalized wave function, which takes the idea of K-side particles in the BCS theory and generalize it as much as possible. And it is very powerful framework, which is used nowadays with powerful supercomputers. and we can describe in a microscopic way the properties of finite nuclei and nuclear matter starting from the nucleonic effective interactions. Okay, so I think this is the end of my lecture today. And if you have any questions, please ask now or later.